This is our first lecture on infinite sets. In order to understand this chapter, it's important that you free up your mind of all previously known concepts about sets, comparing sizes of sets. We're going to start fresh, and if you can do that, you will find this quite interesting, and I think it won't be that hard for you. The first thing that we're going to do is to learn two new terms. Two collections or sets of objects are equally numerous, or you could be thinking the same size, if there is a one-to-one correspondence between the elements of the two sets. In this case, we say that the two sets have the same cardinality. A very simple example would be two sets like the following. Let's say I take the set containing the letters A, B, and C, and I take a set containing the numbers 1, 3, and 6. Well, you can see that those sets have the same size, and you wonder, why in the world do we need a new word like the two sets have the same cardinality? Well, because it's not going to be so obvious when we're looking at infinite sets, so we have to introduce the new vocabulary to be able to include infinite sets in our discussion. But we do say that these two sets both have cardinality. I'll just put card equals 3. They both contain 3 elements. We say that their cardinality is 3. Now, if you were 18 months old, you would not really count those elements. You would just see, a one-to-one correspondence. Your eyes would match these together, and then the third element probably with the third element. You would be looking at that correspondence, and you would know that they were the same size without knowing that their cardinality was equal to 3. So keep this in mind, and keep a very simple picture in your mind. Two sets are the same size. They have the same cardinality if there exists a one-to-one correspondence between them. For example, this is a question in your textbook. The following are two collections of the symbols at and a C with a circle. And it asks you, are they the same? Do they have the same cardinality? Well, unfortunately, I'm looking at the screen here, and I see that it isn't as obvious as it is in the book. They're not lined up perfectly. But you could, if you look in your textbook, you'll see that these are exactly the same size symbols, and you can see one is over the other exactly. But here, I see that when I put it on the slide, it's not so obvious, so I think we need to actually see if there is a one-to-one correspondence by trying to make one, pairing them up in a one-to-one fashion. And it seems that there is. We can pair them one-to-one. Do look in your textbook and see that the way he has it in the text, they're right above each other, and you don't even have to draw lines or match them, because you can just see with your eyes that there is a one-to-one correspondence. So these two sets have the same cardinality. Here again, if you look in the textbook at this problem, you'll be able to answer it without having to actually draw little lines or do anything fancy to see if there's a one-to-one correspondence. But again, when I change this into the kind of file I use for the videos, the R's turned out bigger than the A's. So in order to answer the question, do these sets have the same cardinality, I'm going to actually see if they pair up, because I can't see without actually checking for a one-to-one correspondence. And you can see, of course, that there are 2 more R's than there are @ signs. So these 2 sets do not have the same cardinality. Now, I didn't count them, so I don't know what the cardinality is, but I can see that the set of R's has a larger cardinality than the set of @ symbols. Another question from your text. Suppose a stranger tells you that her telephone number is 245-2345. Would you be able to dial her number and be certain that you would reach her? If so, explain why. If not, explain why not. Identify what additional information you would require to be certain to reach her at home. Okay, well, if you were in an airport and you asked someone for their number and they gave you that number, of course you know why you would not be able to call her. Unless her area code happened to be yours, we need to have the area code. So let's see why that's true. How many telephone numbers could we possibly make? Well, I don't think telephone numbers ever start with 0. So there would be 9 different ways that we could choose the first digit, and any of the other digits, I guess, can be 0. So there would be 10 ways to choose the second, and 10 ways to choose the third, and so forth. 10 times 10 times 10 times 10. So we have 9 times 10 to the 6th, which would be 9 million. 9 million possible telephone numbers. This is just 10 ways to choose the second digit, 10 ways to choose the third, 10 ways to choose each of the 6 digits following the first one. And the first one, there's only 9 ways. And you just multiply those numbers together, and there's 9 million different telephone numbers you could make. But there are far more than 9 million people in the United States that have telephone numbers. So we could say here that there's not enough numbers, not enough 7-digit numbers for everyone to have a number. In other words, the set of all 7-digit numbers has a smaller cardinality than the set of people who have telephones. There is not a one-to-one correspondence between the set of 7-digit numbers. Let's write this down. The set of 7-digit telephone numbers has a smaller cardinality, I'll put card, than does the set of people with phones. So there's just not enough numbers to go around. But if you put the another 3 digits on, then another 3 digits would make it 9 billion. And of course, we do not have 9 billion people, and there's plenty of numbers to go around. Notice he says, discuss the connection between this situation and the notion of a one-to-one correspondence. There is not a one-to-one correspondence between the 9 million telephone numbers that we could make, the 9 million 7-digit telephone numbers. There's not a one-to-one correspondence with that set of numbers and the set of people. In your textbook, you can read this example. Suppose we have a huge barrel of Volvos and a huge barrel of soccer balls. And we want to know if there are more Volvos than soccer balls or more soccer balls than Volvos, or the same number of each. Does the set of Volvos have the same cardinality as the set of soccer balls? So it asks us to devise a method for comparing the barrels without counting the Volvos or soccer balls. So we don't want to count them. That would be one way, but we don't want to count the two. We want to pair them up in a one-to-one correspondence and see if we could pair them up in a one-to-one correspondence. So here you can picture it. We could take out one Volvo from the first barrel and one soccer ball from the second and pair them up. Put it in the trunk. Then we could pair another Volvo from the first barrel with another soccer ball from the second. And if we continue pairing in this fashion, we could tell whether we have the same number of Volvos and soccer balls without ever knowing exactly how many we have. It's just if there exists a one-to-one correspondence between the elements of the two sets, in this case the set of soccer balls and the set of Volvos. If there is a one-to-one correspondence, a way to pair them up, then the two sets have the same cardinality. This compelling concept of comparing sizes via a one-to-one correspondence is the rock on which the whole study of infinity is built. Generally, the most reliable guide to the unknown is a deep understanding of the simple and familiar. Remember, we talked in class about if a baby walks into the room and he sees 4 plates on the table, but there's only 3 people in his family, he and his mom and dad. A little baby, 18 months old, can say, "Who's coming for dinner?" But that baby can't count to 4, and he can't count to 3. So how did he do it? It's in this very simple concept of being able to draw a one-to-one correspondence in his mind between the plates on the table, well, knowing that he could not draw a one-to-one correspondence between the plates on the table and the people in his family. And that's what we're going to do with infinite sets. We have to keep it very simple and remember that if there is a way to pair up the elements of two sets, finite or infinite, they have the same cardinality. They are the same size. We know that the natural numbers, and we have denoted them by n, the natural numbers, let's write one more time what they are. The set containing the number 1, 2, 3, 4, and so on. The set of natural numbers is the first infinite set that we meet. And we meet it when we're quite young. We may not use the word infinite set, but we know that there is no biggest natural number. They just keep going forever. How can we tell if another infinite set is the same size as n? Students tell me all the time they write down every semester, at least half the class or more will answer, even on the test, infinity is infinity. But I want you to know that that is not true. What we are trying to do is compare infinite sets, and we will find that there are larger infinities. They're not all the same size. But we're going to concentrate first on the natural numbers and find other sets that have the same cardinality as n, and maybe we'll find bigger ones. Now you're all familiar with the set of natural numbers. Let's look at some really strange things that can happen with infinite sets that don't happen with any sets that you have ever been familiar with. If we remove, in this first example, if we remove the first 5 numbers in the set, have we made the set smaller? Well, let's see. if we remove the first 5, then what we have is 6, 7, 8, 9, 10, and so on. That's what we have left. Now, let's just write up here the set of natural numbers. I'll do it in a different color. 1, 2, and let's make them smaller. 1, 2, 3, 4, 5, ... Can you see that there is a one-to-one correspondence between these two sets? In other words, actually we're pairing n in the natural numbers. We would pair with, what, n plus 5. This correspondence right here is one-to-one. Therefore, we have removed elements from the natural numbers, but we have not made the set any smaller. The two sets have the same cardinality. Well, how about if we throw out infinitely many of them? Let's throw out all of the even numbers. What's left? Well, it's the odd numbers, isn't it? So let's write down what's left here. I'll go back to yellow. And let's see what's left. The odd numbers: 1, 3, 5, 7, 9, 11, 13, and so on. Infinitely many are left, but we've thrown out, some of you might be thinking, well, we threw out half of them. So wouldn't it make the set smaller? Well, let's see. Let's take in green again, and I'll write the natural numbers here. 2, 3, 4, 5, 6, 7, and so on. Well, no. Look, this is a one-to-one correspondence between the two sets. Now, we don't need to have a formula for it. You can see that if we can list an infinite set, if we can just write it down, the first element, the second, the third, the fourth, the fifth, the sixth, the seventh, etc., that just by making a list, an infinite list, we have paired up these numbers with all of the natural numbers. This is a one-to-one correspondence. So this set of odd numbers has the same cardinality as all of the natural numbers. Now remember, don't make this hard for yourself. We have just seen that it is possible to throw out a few or even throw out infinitely many numbers from the natural numbers, and yet the remaining set still has the same cardinality as the natural numbers. Well, that doesn't always happen. What if we throw out all the numbers greater than 1,000? Well, then what do we have left? We're left with the set containing 1, 2, 3, 4, up to, we threw out all numbers greater than 1,000, so we still have 1,000, and that's all we have left. This is a finite set. It certainly does not have the same cardinality as the natural numbers. It's not an infinite set. It's finite. So in this case, we threw out infinitely many numbers, and we were left with a finite set. So apparently, you can throw out parts of sets and not change the cardinality, or you can throw out infinitely many and be left with a finite set. This is something you've never seen or thought about before because your experience has been with finite sets. What happens if we remove elements from a finite set? Well, let's just take, the set of students in our class. Let's call it S. The cardinality of S is 25. We started with 25 at least. So the cardinality of that set is 25. It's a finite set. Now let's say that 5 students withdraw, drop the class. Well then, of course, the remaining set, the cardinality of the remaining set, becomes 20. So you see that in a finite set, if you remove elements, the set gets smaller. The cardinality is reduced. That's what our intuition always tells us. Throw things out, the set gets smaller. That's exactly what happens in our experience. Infinite sets are creations in our mind. There's no infinite set that you know of except for the set of natural numbers or other sets of infinite sets of numbers, the real numbers, the rational numbers, the irrational numbers, the integers. And we saw in this example that it is possible to throw out elements of infinite sets and not reduce the cardinality. That is one of the fundamental differences between finite and infinite sets.